Thank you. I believe that NISAR is on the edge of a brand new, will bring about a new frontier in Earth science. I went through and took a look at all the different AGU sessions and focus areas in which this mission will touch on, and hopefully by 2020, 2021, we'll have upwards of 11 different sessions in which data from NISAR will be able to contribute to. So can I get my first slide, please? Oh, they're up. With this, I've got to give credit to Paul Rosen. He's the gentleman that's basically overseeing and managing all the scientists and the engineers with basically moving the mission forward. You got the project leads down below, Ralph Dubayah, Brad Hager, Ian Joughin, and then we have the whole science definition team down below. These are the scientists that are working together to bridge the different scientific concepts from ecosystem, cryosphere, natural hazards, all into one comprehensive mission. So a little bit of history with the mission. It comes out of the decadal survey and the NASA climate architecture, in which there's a whole series of scientific questions that were posed in these studies. And they come into three main categories: cryosphere, ecosystems, solid earth science, and new ones that were added by our partners on the mission, which would be ISRO, dealing with the coastal processes within India. And so what the science definition team needed to do is take these different scientific questions. I'll go ahead and pick on volcano hazards. If you've got a volcano, what we were trying to do is ultimately figure out, can we predict volcanic eruptions? Well, that's the question. What measurements do you need to go ahead and begin to address this question? Well, what we need is some way of being able to go ahead and observe the satellites, observe the ground, preferably from space, and with it, we're after geodetic measurements, so we can go ahead and measure the inflation and deflation of the volcano. Well, could some of this be done with optical imagery? And I'll say yes, for some areas. But if you take a look at a lot of the volcanoes in the world, they're in the equatorial region where you've got a lot of atmosphere. So you really need radar as a cloud penetrating technology. So if we take that the next step further for each of the different sciences that we have represented here, the next chart I'm going to show is a complex one where we've got a lot of different requirements. And in looking through each of the different ones, and this is just for solid earth, they map into a particular measurement or a requirement for a measurement. And so in doing this exercise for each of the different key areas, cryosphere, ecosystem, natural hazards, and hazard response, you end up starting to come up with a common set of requirements for a mission. And here's what they are. We've got the L band. We need the L band to go ahead and do vegetation penetration. We also use it for the ecosystem. The S band is the ISRO component, and the advantage with it is it's really good with agriculture. We have a SweepSAR that allows us to go ahead and capture wide areas at the equator. The advantage, or actually in the swath, and at the equator, we're able to go ahead and have fewer orbits that will go ahead and image the full equator, so we're able to have a quicker response time. And you can work your way down the list. One of the ones I think is critical is this one right here with the 30% observational duty cycle. What this allows us to do is image all the land surface and ice surface within a single data collect, and that's for both ascending and descending modes. So we're going to be collecting a lot of data with this particular mission. Let's advance it. So what does a satellite look like? One, we've got it down to a 12-day repeat, and this is at the equator where we're able to go ahead and have interferometric passing. We've got both L band and S band. They are collecting approximately at the same time, but one squinted a little forward, the other one squinted back. And in our orbit, when we pass the equator, it'll be 6 a.m. and 6 p.m. on the ascending and descending sides. And the reason for that time is to go ahead and try to minimize ionospheric noise within the data. From there, we've got a full set of polarimetric capabilities. We've got quad pole, dual pole, selective single pole modes. The S-band has got similar capabilities as well. The resolution. Each of the different sciences sometimes have a different resolution requirement. We're able to go ahead and turn those on and off. But the nominal background mission will be the 20 megahertz, where we have basically 8 to 12 meter resolution in range and 8 meter in azimuth, so that's a long track. We can go at a higher resolution up to 2 to 3 meters. The sweep SAR capability allows us to go ahead and collect in a pretty wide swath. So how is the mission divided? We have ISRO and we have NASA. And on the chart you can see who's doing what. NASA is providing the L-band electronics. They're providing the telecommunication, the GPS, and the data storage, where ISRO is providing the spacecraft, the launch vehicle, and the S-band. And the timeline with this is right now we've got JPL and ISRO developing both of the L-band and S-band components of the mission. And in January 2019, the S-band component will be flown over to JPL, where it's going to be assembled. And once it's assembled, then I think it's October 2019, it'll be flown back over to India, where it'll be bolted onto the spacecraft, put onto the launch vehicle, and if all goes well, October 2020, it'll be launched. So how does the data communication work? ISRO is basically driving the satellite. They're going to be doing all the ground control navigations with it, with all the upload stations on the longitude of India. NASA is going to be doing all the data download, at least when it's outside of the India mask. From there, data will be transferred off to JPL, where we'll have two types of data products. One will be rapid response within 5 hours after the data collect, and the other one will take 3 to 5 days as soon as the precise orbits have been determined. With this, it's going to be 24 terabits of data per day, which works out to 3 terabytes. And here's the cost for it. The cost is free. $0, rupees, and euros. The data is free and open for all users. So what about the tasking? The tasking is built on the 4 key science part. We have deformations, we've got earthquakes, volcanic, landslides, and land subsidence is driving a lot of the solid earth deformation. With the ecosystems, you've got being able to do the biomass calculations as well as change. Cryosphere, you've got the land ice, you got sea ice, and then you have the small scale glaciers with the ice sheets. And we've added the hazard response, and this will work with being able to address a lot of the applications needs. So this is the earthquake response, volcanic response, and this is where we have a lot of low latency data needs for it. With this, in designing the tasking, there's a lot of, I'll say, wrestling, fighting and stuff. We're basically trying to figure out how do we go ahead and merge these different sciences into a single collection. And with it, what we want to do is try to minimize conflict between one data type to another type. And with a lot of discussion, we ultimately came up with having a background mission. Right here, here's the different collection modes. We've got the L-band, and so DP is dual pole, SP is single pole, you got quad pole, and then circular polarization and quasi-quad pole. The S-band got different requirements based from what India is pushing through. And then at the higher latitudes, we have a lot of data. Since the satellite's able to go ahead, there are some areas at the highest latitudes where you've got triple overlap of the data. And so what we're doing is culling these areas where we've got a lot of repeat. That way what we're able to do is go ahead and have even data collection throughout the whole mission. The resolution, you can see for each one, comes down here with sea ice dynamics. They're able to cover a large area, but their science does not require having the high resolution. Next shows a map of where the different data collections are. The green satisfies both the ecosystem as well as the deformation. So effectively, this is the background mission. The small little dots on here are some of the urban and anthropogenic targets that we're putting in, and you can see the distribution elsewhere. One of the things with this mission is it's a right-looking mission for most of the time, but the problem this creates is that there is actually a gap at the South Pole. And so with the right-looking mode, this right here is the gap at the North Pole, small little data gap, the hole there, but at the South Pole, we're missing a lot of Antarctica. And so what we've decided to do is for about 5 cycles out of the 30 per year, we're going to go ahead and flip it around so where it's flying backwards, and we're able to go ahead and fill in this data gap. So we're able to go ahead and maximize the science for the Cryosphere colleagues. This is the project schedule, and I'm not expecting you to read it other than the fact that up at the top we have a time, and each one of these gray lines coming down is a year, with the red line here being launch. What we have on here is it takes a lot to launch a satellite. We've got the project milestones are up here. You've got the payload, you've got flight system. All these different things have their own sets of review that have to be satisfied. We are currently right here, and we're actually a little bit ahead of schedule because we actually had the SRR and MDR last week, which I'll tell you a little bit more about in a moment. Perfect. So this is where we are right now. We have the project completed its mission concept review on October 13th. We passed that, and that set us up for going through KDP-A. KDP means key decision points, and with each phase we have to go through a review to make sure that we've met all the requirements. The last thing we want to do is launch a satellite that is not capable to do what we are seeking it to do. And then we had the implementation arrangement between NASA and ISRO was signed in September. We're about a year to 18 months ahead of schedule with this. We're actually doing quite well. Last week, at the leadership of Paul Rosen, they had the system requirements review, and the mission definition review was completed in Pasadena, and found out that we passed. And so NASA headquarters would like to give Paul Rosen a round of applause with being able to shepherd the engineers, the scientists, and everybody involved to have a very successful review. So thank you. And from that, as soon as you get one thing done, you've got others to go on. Regardless if you've got an AGU or Christmas around, we have KDP-B. Our next major milestone is coming up in February, and we're still on track for late 2020 launch. Things to look forward to, or look for, is the science definition team will be recompeted. Expect out on the street any day, any week. We're actually anticipating it coming out this week. And we're also hoping to be able to add a few new members to the science definition team, but it's completely recompeted. So with my last slide, this is an artist's conception of what the satellite may look like. There's a few design changes that are already not reflected in this, but in wrapping up, I see that this mission, when it's launched, is going to be truly an AGU union mission where we're going to be touching on approximately half of the sessions and focus areas at AGU, and I'm really looking forward to seeing what the next generation of scientists are going to be able to bring to the table. Thank you.